Welcome to today's session. So, in the previous session, we completed Unit 5, which was about queuing theory. Today, we would be starting off with a new unit, that is Unit number 3, Network Models. See, in this network models, basically we can uh, divide this unit into two parts. So, this unit has, in the first part, introduction to network models and uh, optimization problems on network model, right? Network optimization problems. The second part of network model or unit 3 mainly deals with project management and project planning concept of uh, concept using network models. See, which involves CPM, PERT, uh, and project duration handling, mainly dealing with crashing of project duration and project cost. So all this will be handled in the second part of Unit 3. So as of now, I will be starting off with first part of Unit 3, which is Introduction to Network Models and Network Optimization Problems. So what is this network basically? See, networks arises in numerous situations in our daily lives. In our regular day-to-day activities, lot of network scenarios are encountered, like transportation networks, electrical networks, communication networks, production networks, resource allocation as networks, financial planning in form of networks. These are few examples that I can just name. So network representation actually provides a very powerful visual and conceptual aid for portraying the relationship between the components of a system. These systems might be social systems, scientific systems, or even economic systems. So many network optimization models actually are uh, can be said as an implication of linear programming problems. For example, your transportation problem and assignment problem that we have already studied can also be solved. These linear programming problems, we have studied it as special cases of linear programming problem. These problems can also be solved using network models, right? So what is this network? So mainly a network is nothing but a graph, right? In terms of your data structures, whatever we call as a graph is a network here. So network is just a collection of certain number of points and certain number of arcs, or if for you to easily understand, edges, right? In mathematics, in our graph theory, we call it as vertices and edges. Here we call it as nodes and arcs, right? So we shall learn four important types of network problems in the first half of Unit 3, and we will also learn how to solve them. So the problems that we study are single source shortest path problem. We will solve this using Dijkstra's algorithm. Then we will be solving all pair shortest path problem. This we will be solving using Warshall-Floyd's algorithm. Then we will be solving minimum spanning tree problem. This we will make use of Prim's algorithm and Kruskal's algorithm. Then we will be solving max flow problem or maximum flow problem. For this, we would be using the augmented flow algorithm, right? These are some four important network optimization problems that we study in the first part of Unit 3. So before we go into the problems as such, we will be understanding few basic terminologies that we make use in networks. So first thing, what is a network? A network consists of a set of points and a set of lines connecting these points, right? See here, this is a network. Here we have certain number of points 1, 2, 3, 4, 5, 6, 7 and 8, and we have certain number of lines connecting these points. So this entire collection of these points and lines, we call it as a network. So for specific terminology, these points are called nodes. In graph theory, we call it vertices. So the lines are called arcs. In graph theory, we call it either edges or branches. Here in network models, we call it either arcs or links. In graph theory, we term it as edges or branches, right? So arcs are labeled by naming the nodes at either end. See, when I am supposed to address a particular node, I call it as node 1. When I want to address this particular node, I call it node 2. If at all I need to address a link between these 2 points, I will address it as arc 1 comma 2, right? So the naming of the arc is based on the vertices or the nodes to which they are connected. Hope the concept is understood. Fine. Coming to the next terminology, if the flow through an arc is allowed only in one direction, so let me consider node 1 and node 2. If at all I am allowed to move only from 1 to 2 and not in the reverse direction, so if at all I have a restriction on the direction, then it is called a directed arc, right? If the flow through an arc is allowed only in one direction, the arc is said to be a directed arc, and the direction is indicated by adding a arrowhead at the end of the line representing the arc. So we will put a arrow mark to indicate the direction. Okay, a network that has only directed arcs is called a directed network, right? In graph theory, you have learnt it as digraphs, directed graphs, right? So those directed graphs are termed as directed networks here. Directed networks are those which have only directed arcs. Okay, then what is undirected? If the flow through an arc is allowed in either direction, so I can move from 1 to 2, and through the same line I can move back from 2 to 1 also. Both the directions are allowed. Then such an arc is said to be an undirected arc, right? Then we call that arc as an undirected arc. We frequently refer to an undirected arc as link. Fine. We call this undirected arcs as links. So if uh, a network, if a network consists of undirected arcs, then such a network is called undirected network. If all its arcs are undirected, the network is said to be an undirected network, right? Is the concept clear? Shall we move on to the next terminology? Right. The next term that we would be learning is path. A path between any two nodes is said to be a sequence of distinct arcs connecting these nodes. See, let me say I want to know the connectivity between A and F. A to F. A and F are any two nodes on the network. Then a sequence of arcs which connect these two nodes is said to be a path. So in this particular example, A to C, C to E, E to D, D to F is a path between A to F. Okay. A directed path from node I to J is a sequence of connecting arcs whose direction is towards node N, so that the flow from node I to node J along this path is feasible. So if at all it is a directed path, then the flow happens only from A to F. Okay. So next, undirected path. An undirected path from node I to J is a sequence of connecting arcs whose direction can be either towards or away from node J. So I can move from A to G, or the same path can be used to move from G to A, right? A, B, D, E, G is a path either from A to G or G to A. Both way it is permitted. Then it is called an undirected path. Okay. Notice that the directed path also satisfies the definition of an undirected path. See, undirected path, both directions are allowed. But in a directed path, one direction is allowed. So a directed path can be an undirected path, but an undirected path can never become a directed path. Okay, that is what has been specified here. Notice that the directed path also satisfies the definition of an undirected path, but not vice versa. A directed path can be an undirected path, but an undirected path can never be an directed path. Okay, right. We'll move on to the next terminology. Two nodes are said to be connected if the network contains at least one undirected path between them. See, if at all I consider any two nodes, let me say this node and this node. Okay, when I consider these two nodes, if at all I need to say they are connected, there has to be a path between these two nodes. See, here I don't have a direct path or a direct arc between these two nodes. You accept? There is no direct arc between these two nodes, but from this node I can travel through this node and then reach this node. So there is a possibility for me to reach from this node to this node. Therefore, the nodes are said to be connected. Okay, a connected network is a network where every pair of nodes is connected. If at all I take any two nodes, so let me say this node and this node, yes, there is a straight link. This node and this node, yes, there is a straight link. From this node to this node, I don't have a straight link, but I have a connected path available, so it is connected. From this node to this node, yes, I have a direct link. From this node to this node, yes, I have a direct link. So you can check it out with any pair of nodes, right? Any two nodes you consider, if at all I am able to travel between them, either directly or through another intermediate node, then it is said to be connected. Okay, and if every pair of nodes in the network is connected, then the network is said to be a connected network. Okay, hope the concept is understood. Shall we move on? Right. Then till now we only saw the nodes were numbered and there was an arc between the nodes. Now we see one more additional thing here, a number being put on the arc. This actually shows the maximum amount of flow that can be carried on a directed arc or indirected arc, right? There is no compulsion that it has to be a directed arc. Either on a directed arc or an undirected arc is referred to as the arc capacity or the weight of the arc, right? Here 3 specifies that from 0 to 1, 3 units can be carried. Maximum of 3 units can be carried. Okay, therefore we call it a weight of the arc. And a network with weighted arcs, a network which contains weighted arcs is called a weighted network, right? A network which contains weighted arcs is called a weighted network. Hope the concept is clear. Then we define two more terms called path length and path cost. Path length is the number of edges or the number of arcs present in the path. So if at all I consider in this particular example that I want to move from Seattle back to Seattle, right? So I will move to Salt Lake City, then to Chicago, then to Dallas, then to San Francisco, and back to Seattle, right? So how many arcs are involved? So this is one arc, arc 2, arc 3, arc 4, arc 5. So 5 arcs are involved in the path. Therefore, the path length is said to be 5, right? The path length is said to be 5. Then what is path cost? Path cost is the sum of the weights or the costs of each arc. Okay, here I have considered the arcs. So on the arcs I will have certain weight. So if at all I add up all those weights, then it is called a path cost. Here in this particular example, 2 plus 2, 4, 4 plus 2.5 is 6.5, 6.5 plus 3 is 9.5, 9.5 plus 2 is 11.5. So the cost of the path is 11.5. Hope the concept is understood. And how do we write this path? So this path will be represented as a set, right? SEA to SLC. I have just written the short forms. SEA to SLC to CHI to DAL to SFO to SEA. Fine? Understood? How a path is represented? What do we mean by path length and what do we mean by path cost? Is the concept understood? Okay. And as we are computer science students, we will be interested in how these networks are represented in memory also. That also we have to take care. So before that, we will see a difference between a simple path and a cycle. A simple path has no repetition of vertices. So in this particular example, Seattle is repeated twice. So it is not a simple path. If at all I had stopped at SFO, see, this vertex is used only once, this vertex is used only once, this vertex once, this vertex once, this vertex once, then it would have been a simple path. But we have used settle twice, so it becomes a cycle. A simple path repeats no vertices. A cycle is a path that starts and ends at the same node. Fine. There can be a repetition of vertex. A simple cycle is a cycle that represents no vertices except the first vertex as also the last. Only the first vertex will be repeated twice. It will be the last vertex as well. Then we call it a simple cycle. Okay. So coming to the network representation in memory. So what exactly is a network? So it is a list of vertices and a list of edges, right? Or in network models, we call this as nodes and we call this as arcs. So it is a list of nodes and a list of arcs. So how can we represent it in memory? There are two methods. When we have a static requirement, then we make use of matrices or an array. If at all we have a dynamic requirement, then we make use of a linked list, right? When we make use of static memory requirements, so a set of arrays will be used, two-dimensional arrays, which is termed as a matrix. So a 2D matrix of vertices will be created and we call this as cost adjacency matrix. And if at all we are using a linked list, then we call it as cost adjacency list. For a very simple example, we will see how cost adjacency matrix is written and how cost adjacency list is written. So coming to cost adjacency matrix, so consider a network here. We have three nodes A, B and C. So the resultant matrix will be a 3 cross 3 matrix, a number of vertices cross number of vertices matrix. Okay. So I will have a ABC matrix. So if at all the weights are given here, let me say the weight from A to B was 2, then in the cost adjacency matrix from A to B I will write it as 2. Okay. Then from B to A, if it was 1, from B to A I will write it as 1. From C to B it was 3, then from C to B I will write it as 3. Rest, wherever there is no path available, I will put it as a 0. A 0 represents no path or no weight. Okay. So this becomes your cost adjacency matrix. So then how do we represent the network in form of a cost adjacency list? So I'll consider the same network. So I will have a array which is connected to a linked list. So node A is connected to a linked list. This linked list will have how many ever outgoing nodes are there, or how many ever outgoing vertices are there. We will have to look. So from A, how many outgoing vertices? Only one. So it will be connected to one node. So in this node, we will write two things. One is it is connected to which node? B, and we will have to write the cost. So if at all the cost was 2, I will write it as 2. So in this linked list, if at all I have one arc, then I will have one link and it will contain B comma 2. So now coming to B, I have only one outgoing node, so it will be connected to one linked list. So I had considered the cost as 1. So here in this box we will contain, what do we contain? The destination A and the cost 1, right? So now coming from C, I have only one outgoing node, sorry, outgoing arc. So in the cost adjacency list, I will have only one linked list, which will contain, what does it contain? The destination B with cost 3. Hope the concept is understood. Isn't it simple? Right? So today we wind up the class here with all the basics and the terminologies that are required before solving the problem. In the next session, we would be dealing with the first problem, that is single source shortest path problem, which is solved using Dijkstra's algorithm. Till the next session, have a nice time, enjoy. Thank you for your patient listening. Thank you.